The last component we will cover in this module would be metal alloys and defects. Later on, it's going to play a very important role when we talk about strengthening material, talking about enhancing its corrosion resistance and things like that. So this is going to be very helpful for us, especially later on. But what you guys need to keep in mind is that in real applications, right? Pure metals are rarely used in engineering applications. There is an exception. So typically for corrosion resistance, for the strength, and to be honest, and I feel like this will combine pretty much every single application, engineering application. You either want something strong corrosion resistance, or perhaps even to tailor materials. We usually go with alloying, right? Because it allows us to take a material, or perhaps a few materials, and once you combine them, you actually typically you enhance the properties of each of the materials, and you come up with something that is a lot stronger than each of the materials on their own. To be honest, now I'm thinking there are so many other unique properties that you will cover in this course. The only exception is going to be the conductivity. Right, if I am to pass the electricity, I don't want any defects in there. And whenever you introduce different elements together, you already know that the radius is different. So, of course, having an alloy will impede the electron flow. You don't want to have electricity passed through a perfect, ideal, pure metal, right? But typically for engineering applications, we use metal alloys. Okay. Now, alloy may contain two or more metals and sometimes non-metals, and it doesn't have to have even two. I will give you an example of like a binary alloy brass. We've already mentioned it before. Brass is 70% Brass is 70% copper and the rest 30% is zinc. This is an example of a binary alloy, meaning that there are only two elements in there. Now, but I can also give you an example of Inconel 718. This element is usually, we call it a nickel based because the more than 50% of this alloy is made out of nickel, right? And then this is used for jet engine parts. Uh, that specific alloy has 10 elements in the nominal composition, and you guys can see it is listed in the bottom right corner. And you will probably notice that not only metals, it also has a non-metal elements such as carbon, right? Okay, so what is an alloy, right? How do I define it? What does it look like under the microscope and things like that, right? Now, so solid solution is an alloy that can exist in a single phase form, okay? So what it means is that if I am to look under the microscope, it will look, this is what you guys actually see on the left side, left bottom corner. This is an alloy, and the way we describe it, it's a single phase. And right away, you guys see those lines? Those are just the grain boundaries. But if I am to take, so these lines are grain boundaries, right? That separate grains. But if I am to take one grain, right? For example, let me take this one because it's very well defined. And let me zoom in. You guys can see that it's a one phase, right? It's all look the same. Yes, I see a bunch of grains. They have different shapes. And of course, they're separated by the boundaries, which are the black lines. But the grain itself, wherever I go, left or right, it's all the same color. And in a sense, it is same composition. And this is what we call a solid solution. And an example of such is going to be a low carbon steel. An example of such is going to be a low carbon steel. Now, metal alloy can also be a mixture. And Whenever we talk about a mixture, it's usually something that looks that has multiple phases. And this is exactly what you see in the bottom right corner. We're looking at two phases. I can clearly see that I have a phase that is darker in color, and I have a phase that is lighter in color. And this is actually a medium carbon still. And usually when it happens is that phase one is different from phase two in terms of composition, and that's why they look different under the microscope. And that's basically the difference between a solid solution and a mixture, right? Now, solid solutions, okay? In solid solutions, the impurity, or we also call it a solute, are atomically dispersed inside the host in a single phase, just like we've seen on the picture, right? So usually, so if you look at it, you wouldn't be able to tell that that's not a pure metal, right? Yes, you will see grain boundaries, those lines, but you will see them anywhere, right? But in a sense, it looks like a single crystal, but it does have impurities in there, and we also call impurities as a solute. The matrix, perhaps I shall say it now, matrix itself, right, is your solvent, and impurity or a dopant is your solute. Okay. Now there are two types of solid solutions. And those are, it is relatively straightforward. Substitutional, that means that one or two, I shouldn't say how many, solute atoms are replaced with solvent atoms, right? Um, so in a sense, is that instead of seeing this lighter blue everywhere, what actually happens right in here, right? We're taking one of the solvent, right, matrix atoms, and we replace it with a solute. Okay, now it could also be interstitial. The solute atoms, they force themselves into available spaces, right? And that's why we call it interstitial site, right? An example is going to be actually the carbon and iron. So you guys will see is that, and I will actually draw it right here. You see this available space, okay? Carbon is actually small enough and it can be fitted in that interstitial place. And so I can squeeze them there. And that's exactly what you're looking in this region. But you do guys see that once it is squeezed in there, the iron elements, they are a little bit distorted. And this is something that we have to keep in mind is because later on, this distortion has a very significant impact on the strength of your metal. And this is sometimes that's how we make the material stronger. I'll go back to that point one more time, but I do want you to keep in mind is that whenever we have something like that, not necessarily just with the interstitial, right? It's just easier to fit to explain it with the interstitial. For the interstitial alloy to actually happen, you can't make it with any element. The element has always to be smaller than the available voids in your solvent, right? And whenever you do squeeze something in there, the lattice surrounding this void, or it's not a void anymore, now it's occupied by the impurity, but there is a little bit of a distortion. Again, engineers found a way to take advantage of that. Uh, Now, substitutional solid solutions. Let's look a little bit closer at them, right? Now, we already know that the solute atoms substitute solvent atoms in lattice, right? Now, the solvent structure remains unchanged. Yes, for the most part, right? Actually, no. The way I phrase it here, yes, the solvent structure remains unchanged. No, for the most part. Why? Because the solvent lattice might get slightly distorted if there are differences in the atoms. And what I mean by that, there could be the difference in size, there could be a difference in electronegativity, right? Because you're basically plucking out some of the elements and you introduce something new. Again, you can't fit anything you want, right? Because there's a specific spot that is available. And again, the solvent structure remains unchanged for the most part. However, you may introduce certain distortions, right? Now, question is how much can I squeeze in there, right? Let's say, and how do I choose those elements? Can I choose any element? And if there are only specific elements that I can, is there a solubility limit? Is the 100%? Can I actually start with lead and start replacing atom by atom, swap it with nickel and get to a pure nickel, or perhaps I should give you an example of tin. Is it possible, right? What is the solid solubility limit, right? So the solid solubility limit, or it's basically the impurity weight percentage in the solvent, right? It can vary actually from 0 to 100%, right? By 0, I mean I'm starting with something that is pure. By 100, that means I actually, by swapping, went from one material to another one, right? But that limit is determined by Hume-Rothery rules. They are actually very, very simple. Well, and they do make sense, guys. Because even if without giving you this, if I asked you right now, what do you guys think would play a role in defining that limit, you would tell me these things. Once you think hard, you would be telling me these rules, right? Well, first, it's going to be the similarity in size, right, between the solute and the solvent. Um, and the more similar they are, the higher the solubility limit, right? The more you can squeeze in there because it gets unnoticed. Next is going to be the similarity in crystal structure, right? Of course, if you are taking something that has a similar structure, let's say both are BCC, both are FCC, they don't have to be the same. It's very important, guys. They don't have to be the same. You can have a BCC and FCC that are, excuse me, being mixed together and working fine. There's also a similarity in electronegativity. In case you forgot, I will remind you electronegativity, that is the degree to which the metal tends to pull the electron its way, right? And then there's also the similarity in the number of valence electrons. So keep in mind those: size, crystal structure, electronegativity, and valence atoms. Historically, I've been asking something like this either in the quiz or in the exam at least once, okay? Now, guys, let me give you an example like this. Uh, let's look at copper and nickel, right? Because this is the best. The solid solubility is 100%. And let's look at what we are mixing here. Well, the atomic radius difference, it is present there, but it is exceptionally small, right? It's 2.3%. Okay, there is no electronegativity difference. They have the same crystal structure and they have the same valence. And this explains how you can start with a pure copper and replacing atom by atom. That's not how we do it, but in reality, you could do that, get to a pure nickel, right? And from pure nickel, you can actually go backwards to a pure copper, right? But let's say if I am to look at the example, this was going to be a good example. Same copper, but this time instead of nickel, I'm trying to dope it with zinc. Okay, if you look at the atomic difference, it is still pretty acceptable, right? It's about 4%. There is a slight electronegativity difference. However, there's a significant crystal structure difference, right? We are looking at FCC and HCP. HCP is your hexagonal closed pact. Hopefully, you guys remember what it looks like. And they do have the same valence, right? But these differences, once you have a difference here, you have a difference there, the solubility limit drops from 100% to 38%, right? It's a very significant difference, meaning that the maximum of zinc that you can dissolve in pure copper is 38.3%, right? Now, if we're looking at the copper and lead, again, something to point out is that there is a large atomic difference, right? Large atomic difference. There is a rather significant electronegativity difference. They do have the same crystal structure, right? But think about it. Once you envision this FCC, right? It's one cube is 40% bigger than the other one, right? And so this is why the solubility limit drops below 1%, right? It's 0.17%, okay? Um, while I have these following statements in on the slide, they do apply to the majority of alloys, right? So the main factor is going to be the difference in size, right? And it makes sense. The more similar they are, the easier it is to blend for them, right? Now, the second important factor is electronegativity difference. The third important factor is structure difference. And then the fourth is valence difference. Not necessarily I would rank them in this order, but usually the size is something that I can tell you right away whether you can have a substitutional, that's also important, solid solution or not, right? Now, interstitial. Now, with the interstitial, it's going to be slightly, perhaps a bit more straightforward. because the solute, right, the impurities reside between the voids. Well, they're not between the voids, they are actually inside the voids, right? Why would I say between the voids? Um, Yeah, that's probably no, they are in the voids, right? Because guys, they occupy, this is where they occupy. This is where they occupy, right? Perhaps I should put across. So I think the proper way to say it, the correct way to say it is not the between the voids, but they fit in the void, right? So perhaps I should say in the voids. This is reside in between. I was supposed to delete between, pretty sure. Anyway, now, for that to occur, right, the solute atoms must be much smaller than the solvent atoms. And it makes sense, right? Because you gotta squeeze something into this void and you're gonna choose something that is smaller than the void, right? Or comparable to the void. Um, um, I'm running ahead of my own thought. What I highlighted says, what I just said is that the solid atoms must be smaller than the size of the void, right? Or we also call it interstitial site. But they also must be smaller than the solvent atoms, but it kind of comes together, right? Um, Now, one thing to keep in mind is that they do cause local strain, and while it is not necessary, engineers do know how to take advantage of that. And later on, I will show you something like this. For electricity, for conductivity purposes, that would be a no, right? Because it's going to be something that will impede the electron flow because there's going to be a distortion. But for a lot, there are other applications that actually benefit from this local strain, okay? Now, a little bit about the crystalline imperfections or crystalline defects, right? So, crystals are never perfect, okay? And almost always they contain imperfections, right? Now, these imperfections, they can affect the properties of the material, such as mechanical, optical, chemical, electrical. We're not going to go deep into optical, chemical, and electrical, but we will talk quite a bit about the impact of these imperfections onto mechanical. And what I mean by that is strength, okay? Um, Now, all of the crystal imperfections can be classified into main four categories, and we do that taking into consideration their geometry and shape, and it's going to be very easy. Zero-dimensional point defects. Point defect, let me guys show you an example. Right in here. Do you guys see this vacancy? That's your point defect, right? Now, what else? If we're looking at the one-dimensional, these are line defects, and it's kind of like a dislocation, and I'm about to show you examples of that. We can also have two-dimensional surface defects and three-dimensional volume defects or cracks. In this course, we are mostly interested in point defects and line defects because those two will play a significant role in the mechanical properties of our materials. Now, point defects. It is either vacancy or it can also be interstitial seed, right? So what is a vacancy? Just as I showed you a minute ago, it's simply a missing atom, right? Right here. Boom. That's a vacancy. That's a point defect. Um, Now, vacancies often form during solidification or due to mobility, diffusion of atoms. So either you have a diffusion of the atom within a material, or it sometimes happens during the solidification, right? The atom didn't make it to the spot, and the spot is now open and available. This also may happen due to plastic deformation. Plastic deformation, I want you to envision, is that when I plastically deform something, meaning that um, I create a permanent slip, right? Like if I fix my material and I apply a lot of pressure and I can actually like mm, create a slip. This can result into a vacancy. It also happens during rapid cooling. Now, something to keep in mind is that vacancies, they are not actually stable. It's not like they're always there. They do have an ability to move across the lattice. So basically, they pop here and there. Again, we do know how to take advantage of that. And sometimes, since we know that we can have a situation where your atom actually occupies interstitial site, right? We can end up having this interstitial, say, defect. So meaning it's an example right here. So it's the atom is not in its regular position, but rather is taken in interstitial site. And that's how under the microscope we will see the distortion, and we call it interstitial C defect, right? Now, if we ought to look at the ionic crystals, right? Now, because you guys understand what the ionic crystal is, right? Basically, we have this positively charged and negatively charged. You have a cation and anion. Then there we actually have point defects that they have two different types, right? Um, and we call those a Schottky imperfection and a Frankel. So the Schottky imperfection, if it's two oppositely charged particles are missing, meaning that you now have a die vacancy, right? And it's an example right here. You can see how you're missing this guy right here and you're missing tiny guy right here. So you're basically missing a cation and the anion, right? So it's a die vacancy. Now, the Frankel imperfection happens when you have a cation that moves into interstitial site where it does not belong. It's right here. So this guy moved from here to here where it does not belong, and we call it a Frankel imperfection. In ionic crystal, the presence of these defects actually increases their electrical conductivity. So again, usually when we look at the defects, we should not think about defects as something that is negative. There are so many applications where we found a way to take advantage of it, right? The whole revolution in transistors happened only due to one simple skill that people found out, and that is doping pure semiconductors, taking silicon and adding something into that. And that launched us into a whole new era and revolutionized the world, right? Now, line defects. So when we talk about the line defects, right, it's a two-dimensional. We also call this dislocations. And you will often hear me saying instead of line defects, I would always say dislocations because that's kind of the proper way to say that. So these are lattice distortions that are centered around the line, right? And we call it a line defect. It could be either an edge dislocation, a screw dislocation, or a mixed dislocation. And I think uh, I actually have really good examples right here, right? So the edge dislocation is formed when an extra half plane of atom is inserted into the lattice, right? And this is an example right here, okay? So do you guys see how the metal, like if you ought to take this plane and now remove it, then you're gonna have a perfect crystal, right? But now, because you do have an extra half plane, right? You basically end up with some compression, right, above, and then you have some kind of distortion, or I don't really know how the best way, well, it's called a tensile stress when something is stretched, right? Some stretching right below this spot, right? So compression on top and then stretching at the bottom. Now, the screw dislocation is formed due to the application of the shear stress. And one of the ways to think about it, so I want you to look at this perfect crystal, figure A, and now I want you to think of a screw that kind of like you're screwing something into the crystal, and we call it a shear stress because there's a little bit of a slip. And we call it a screw dislocation, right? Because you guys can see that there is like this step-like figure that is now present at the bottom because we're kind of like screwing it in, right? And then sometimes you end up with a mixed dislocation, right? And here's an example of such, right? Um, And usually, we actually, in crystals, systems are very complex, right? And again, they are never perfect. But in here, you guys clearly see that here's your edge dislocation, right? Because you have this extra half plane inserted right there, right? And that's why you have compression above and then stretching below it. And then right in here, you have this screw, right? It's kind of like a shear stress. One plane is shifted with respect to the other plane. Um, Now, a little bit more on the planar and planar or linear defects, and specifically the grain boundaries. I already mentioned today a little bit, and it's easy to understand. Whenever you guys have a material, right, a liquefied material that you now solidify, you have these grains that grow, right? They nucleate and then they grow in size, and eventually they basically touch each other. And so usually you are able to see that as a grain boundary. And perhaps the best example is to show you something that I've already shown you when I was showing you the alloys. Yeah, right in here. These lines, again, I'll draw them again. These are your grain boundaries, and they do play a very important role in the strength of the material. And of course, they are seen here as well, right? It's just the resolution of the image is not as clear, but the grain boundary is going to be the line between the white and the gray, right? For this specific two-phase mixture. Um, the last thing I will show you about the I'll say it now, however, I won't expect you to know it yet because we're going to have a whole lecture dedicated to it. But I will say that the grain boundaries, they restrict the plastic flow. So what it means, if I am to take the material, right, let's say if I have a material and I'm applying a shear stress, right, so I'm trying to like squeeze one plane with respect to the other, these grain boundaries, they impede that flow, the plastic flow. And in a sense, they strengthen the material, they prevent the flow, meaning that your material can withstand a significantly higher shear stress, right? And then sometimes we also can look at twin boundaries. It is relatively rare. However, the twin, that means that it's kind of like a mirror-like. So if you have a twin boundary, and if you hold it, if you fold it with respect to the twin boundary, you basically have a mirror image of structure, right? It is relatively rare, but I figured I'll share it with you. It's kind of cool to see. I've synthesized several materials that did show these twin boundaries. It's very unique when you see it under the microscope. It's almost like a magic moment, right? Because the nature is very, very perfect. But just as grain boundaries, they're going to play the same role. They will strengthen the metal. With this, we conclude our learning module number 3.